Hi, this talk is on new sublinear algorithms and lower bounds for LIS estimation. I'm Nithin Varma. I was a postdoc at University of Haifa. I'm transitioning to being a faculty member at Chennai Math Institute. This is joint work with Ilan Newman, who is my postdoc advisor at University of Haifa. Here is an outline of the talk. I will first define what we mean by the longest increasing subsequence, abbreviated LIS, discuss a brief history of LIS estimation, and also mention its connection to property testing sortedness of arrays. We will then discuss our results and give an overview of the techniques used in the design of our non-adaptive LIS estimation algorithm. I will finally conclude with some open questions. The longest increasing subsequence, or LIS for short, given an array of length n, is the longest non-decreasing sequence of array values. Determining the length of LIS is a fundamental problem in computer science. Classical exact algorithms are known for this problem that run in nearly linear time. Our focus, though, is to design sublinear time approximation algorithms for LIS. Sublinear time algorithms for LIS estimation have been studied. One of them is a polylog n query algorithm by Parnas et al. And Ilan et al. That gives plus minus n over 2 approximation. An improvement in the approximation guarantee to plus minus delta n was obtained by Sachs and Seshadri in a seminal work where they gave a polylog n query algorithm for constant delta. I would like to emphasize the fact that this result is meaningful only when the length of LIS is at least delta n, where n denotes the length of the input array. These algorithms are adaptive, which means the queries made by the algorithm may depend on the answers to previous queries. Additionally, the query complexity of the Sachs-Seshadri algorithm stops being sublinear as soon as delta is less than or equal to 1 over log n. Coming to multiplicative approximation, let lambda denote the fractional value of LIS or LIS divided by n. Rubinstein et al. Recently gave a non-adaptive algorithm with query complexity O tilde root n, poly 1 over lambda, that outputs an omega lambda cube multiplicative approximation. For your reference, I have given here what we mean by a multiplicative approximation on the slide. Very recently, in a work independent and parallel to ours, Mitzenmacher and Sedegin gave an omega lambda to the epsilon multiplicative approximation algorithm for LIS for epsilon in between 0 and 1, whose complexity is sublinear in n but worse than root n. The problem of LIS estimation is intimately connected to the problem of sortedness testing. The Hamming distance of an array to sortedness or monotonicity is the minimum number of values that need to be removed from the array to get a non-decreasing subsequence. Abbreviating distance to sortedness as ds, we get that ds plus lis is equal to n, which denotes the array length. Property testing sortedness of real-valued arrays has been widely studied. There are several testers known, and specifically the problem here is to, given an array, to distinguish with high probability between the cases that the array is sorted versus the case that the distance to sortedness of the array is at least delta n for some parameter delta. It is known that LIS estimation is at least as hard as sortedness testing. Our focuses in this work are twofold. One is that we do not know any non-trivial lower bound on the query complexity of LIS estimation. I stress on the term non-trivial because there is a tight lower bound of omega log n on the query complexity of sortedness testing by Fisher, which trivially translates to a same lower bound on LIS estimation query complexity. Secondly, we ask the question whether n, or the input length, is the right input parameter to express the complexity of LIS estimation algorithms. This question is motivated by the fact that for Boolean arrays of length n, plus minus delta n error LIS estimation is possible with 1 over delta square queries. In contrast, for real valued arrays, the best algorithm that provides the same approximation guarantee is the polylog n query algorithm of Sachs and Seshadri. Additionally, for testing sortedness, Pallavur et al. Studied parametrizing the complexity in terms of number of distinct values in the array instead of the array length and bridged a similar gap between Boolean and real valued cases. These are the two questions that we consider in our work. Our first result is a lower bound on LIS estimation. Essentially, it says that no non-adaptive algorithm that makes polylog n queries can estimate LIS up to an additive error of plus minus delta n for all constant delta. This is the first non-trivial lower bound on LIS estimation. It additionally shows that adaptivity helps in LIS estimation because there is an adaptive algorithm by Sachs and Seshadri that for all constant delta makes polylog n many queries. And our lower bound rules out the existence of such a non-adaptive algorithm. Our second result is a plus minus delta n approximation algorithm for LIS whose complexity is parameterized in terms of R, the number of distinct values in the input array. Our algorithm makes O tilde R over delta cube uniform and independent queries. To contrast with Sachs-Sheshadri, this is the only sublinear time algorithm providing this approximation guarantee when delta is smaller than 1 over log n and R is little o of n. Moreover, our algorithm is non-adaptive and makes uniform and independent queries. Our next result is a non-adaptive LIS estimation algorithm providing an omega lambda multiplicative approximation guarantee where lambda is LIS over n. Our algorithm makes O tilde root R non-adaptive queries. Our algorithm provides better approximation guarantee as compared to Rubinstein et al. And when R is equal to n, the running time of our algorithm or the query complexity of our algorithm is identical to that of Rubinstein et al. We would like to also point out that additionally, our algorithm is much more general as its complexity is parameterized in terms of the number of distinct values in the input array. And it is strictly better than Rubinstein et al. In terms of the complexity when R is much less than n. We now discuss some consequences of our results to tolerant and erasure resilient testing sortedness. We already saw what testing sortedness means. Tolerant testing is a related model introduced by Parnas et al. In tolerant testing the property of sortedness, the problem is to distinguish between the cases that the distance to sortedness is at most alpha n from the case that distance to sortedness is at least alpha plus delta n for parameters alpha and delta. And this problem can be solved if one can estimate LIS to within plus minus delta over 2n. The erasure resilient testing model introduced by Dixit et al. Is a model that falls somewhat in between testing and tolerant testing. And for the property of sortedness, Um, this testing question asks us to distinguish between the cases that given an input array where some of the array values are erased, um, you have to distinguish between the cases that the non-erased part of the array is sorted from the case that the non-erased part of the array has distance at least delta n from sorted for a parameter delta. From a sequence of works, it is known that in general, tolerant testing is strictly harder than erasure resilient testing, which is strictly harder than testing. And these models are defined for, for more like arbitrary properties, not just sortedness. And this is what we mean by the following statement. There is a property for which tolerant testing is very hard, but for the same property, erasure resilient testing for comparable parameters is very easy. And similar statements hold for other inequalities. The lower bound that we prove on additive error LIS estimation is in fact a lower bound on tolerant testing sortedness. And we actually get super polylog lower bound on tolerant testing sortedness. In contrast, we show that erasure resilient testing sortedness can be performed non-adaptively using big O of log n queries, thereby separating tolerant and erasure resilient testing models for the well-studied property of sortedness for non-adaptive algorithms. So here is the consequence of our results to separating tolerant and erasure resilient testing models. Our result resolves an open question posed by Raskolnikova et al. About coming up with a well-studied property separating these two models. In the rest of the talk, I will discuss our non-adaptive algorithm for LIS estimation that outputs omega lambda multiplicative estimate to LIS length. And it is also, our algorithm is parameterized in terms of the number of distinct values in the array, and it makes O tilde root r poly 1 over lambda non-adaptive queries. For the purpose of the talk, I will simplify the theorem statement a bit and try to give you some of the ideas involved in the algorithm and analysis of this simplified statement. We take the special case, or maybe we take the special case of the array having n distinct values, that is r is equal to n, and we will describe an O tilde root n poly 1 over lambda query non-adaptive algorithm. We also assume that we know a lower bound lambda on LIS over n. The first main idea in our algorithm is to view the array as a grid of index value pairs of points. This naturally defines a poset on such points. Consider the points P, Q, and R here. The point P is defined by some index and its corresponding array value. We say that the point P is less than or equal to point Q in this poset ordering because point Q lies to the northeast of point P. And we say that point Q is not comparable to point R. And LIS is a longest chain in this poset of points. A rectangular subregion of this grid is a box. In this picture, consider the box B. The width of this box B is the number of indices that this box spans, and the density of the box B is the number of points falling inside the box normalized by the width of the box. The first step in our algorithm is to partition the range of the array, which is the y-axis of this grid, and also the x-axis of the grid into roughly root-n equal parts, by which I mean the following. We divide the range into horizontal layers, so L1 through L root-n, L theta root-n, which are rectangles of roughly equal density. We also partition the index set into theta-root vertical stripes. And we show that such a layering is possible with high probability using theta tilde root non-adaptive queries in the paper. I do not show how. In the paper, we show a procedure for doing this. Now, such a layering defines several boxes in the grid. It partitions the grid into small regions, small boxes, and there is a natural poset on the boxes. Specifically here, the box B1 is at most or less is comparable and less than or equal to B2. B1 is less than or equal to B3. B1 is less than or equal to B4. However, B4 isn't comparable to B2, and B2 isn't comparable to B3, and B4 isn't comparable to B3. You get the picture, right? And the boxes through which the LIS passes is a chain in this poset of boxes. The set of boxes through which LIS passes is a chain here. This should be clear. As a next step, we mark in each vertical stripe, we mark boxes that contain at least a beta fraction of the points in its stripe. Let's say we mark them green. For the purposes of the talk, we make an additional simplifying assumption that each green marked box has roughly beta fraction of the points in its stripe. Specifically, if you look at this first stripe S1, each of these two green marked boxes contain roughly beta fraction of the total number of points falling in this entire vertical rectangle or vertical stripe. We additionally show that such a marking is possible with theta tilde root non-adaptive queries, and after this marking, a constant fraction of LIS is present in these marked boxes. This is a claim we show in the paper. This implies that it is completely okay to ignore the unmarked boxes because most of the LIS belongs to the marked boxes. So we do that. Now a strategy is to estimate the LIS somehow in each chain of marked boxes and output the maximum among these values. The issue here is that there are too many chains. In fact, one can come up with examples where the number of marked boxes is quite small in the whole grid. However, there are exponentially many, exponential in n, or in root n, many chains among the marked boxes. To fix this issue, we repeatedly remove large antichains from the grid. Specifically, we remove antichains of size at least 1 over lambda from the grid. And this would mean that at the end of this procedure, we do not have any antichain of size larger than 1 over lambda, which by Dilworth's theorem implies that the poset can be covered with at most 1 over lambda disjoint chains. And we prove in the paper that a constant fraction of LIS is still present in the union of these 1 over lambda chains of boxes. That even after this anti-chain removal, we still have a considerable amount of LIS left. And now we simply estimate LIS among each of these 1 over lambda chains and output the maximum. And this can be done. We will see how. During this procedure, we incur a loss by a factor of lambda to the LIS, which constitutes our approximation guarantee. Okay, coming to estimating the LIS in a single chain, consider this chain depicted here by means of shaded boxes. We first partition this entire chain into vertical and horizontal chains. Here, The horizontal chain consists of those boxes that are shaded with a solid blue, and the vertical chain consists of those boxes that are kind of shaded with a hatched yellow. We can then estimate the LIS in the vertical chain and horizontal chain separately. Consider the vertical chain. It is a disjoint union of vertical blocks uh, that do not share a stripe with each other. Now, we show that in our paper that if LIS in the vertical chain is at least a lambda fraction of the true LIS, then many such short vertical blocks exist. Which means there is a simple strategy to estimate the LIS. Uh, we sample a small number of vertical stripes or vertical blocks from among these yellow blocks. We exactly compute LIS in each one. This is possible because our query budget is root 10 and a vertical stripe has at most root 10 points. And estimate the LIS in vertical chain using these values. This additionally, we show that this can be done non-adaptively by making theta tilde root and poly 1 over lambda queries. And one can do something similar, however, more sophisticated for estimating the LIS in horizontal chains. And by summing these two values, we estimate the LIS in the entire chain. So here is what we saw so far. We discussed some of the key ideas used in a root-n query non-adaptive algorithm to approximate LIS length within a factor of lambda. We made several assumptions on the way. Removing these assumptions require more arguments. And in the paper, we show a much more general result. We show a O tilde root R query non-adaptive algorithm to approximate LIS length within a factor of lambda for arrays with to most R distinct values. This is a more general result and ends up using more sophisticated ideas. In particular, it uses the other non-adaptive algorithm we developed in the paper as a subroutine. Here is a short summary of our contributions. We provide the first non-trivial lower bound on the query complexity of LIS estimation algorithms. We present non-adaptive LIS estimation algorithms with better approximation guarantees than state-of-the-art algorithms, while also providing similar running times. We parameterize the complexity of sublinear time algorithms for LIS estimation in terms of the number of distinct values in the array. And we also separate erasure resilient and tolerant testing models for the well-studied property of sortedness, thereby resolving an open question. Here are a couple of open problems. One maybe most important open problem in this area is to come up with strong lower bounds for adaptive or non-adaptive LIS estimation tasks for either of the approximation guarantees, either the multiplicative approximation situation or the additive approximation situation. The next question would be to improve the algorithm of Saxon-Shishadri, maybe in terms of query complexity, or perhaps somehow reducing the adaptivity involved in the algorithm. That will be all. Thank you for listening. Thank you.